disadvantages. If the model is inaccurate, the performance could be hurt. And this is a real thing, right? If you start planning with an inaccurate model, you can go wrong very quickly. That's sort of obvious. So planning can be computationally expensive. So these model-based techniques, often you're looking at a trade-off between computational time and experience efficiency, where experience efficiency is how much data do you collect from the real world? How much experience do you need from the real world? Whereas if you have a model, you can do a lot of stuff without new data by just churning on a planning algorithm or doing some other type of simulation in the algorithm itself. For very complex environments, a model may be harder to learn than the policy or value function. This you can imagine. This seemed to be the case for things like Atari early on. I think we're learning how to maybe reverse this, but we'll see as we move ahead. All right, so now what I want to do is talk about some of these choices. So the model choices, representation. Well, I'm gonna talk about 3 representations. One is tabular models. We already talked about those. Much of the theory of RL is in this setting, and you can think of the tabular model as sort of corresponding to the assumption that your whatever modeling method you're using can model any environment whatsoever, right? So it's sort of assuming that there's no bias or assumptions on what the model space is. You can model any MDP. So we're going to talk about this and even show that it's not dead in the water, even though it's tabular. The other type of technique, and this is sort of really near and dear to the hearts of ICAPS people. So structured and symbolic models. These are things like strips and PDDL. You pick some language to represent the environment in, and you try to learn. Learn a representation of the environment in that language. And this is just some example from the blocks world for strips. Well, the issues that you run into very quickly is, what if the language isn't well matched to the world? You're going to have some trouble. And also, where do the symbols come from when you have very perceptual inputs? So those are some challenges with that approach, as much as we love them. The other type of model, which is maybe the most popular and common these days in model-based reinforcement learning, is I'm going to call it a black box simulator. It's just something like a neural network that takes in the state, the current observation, and an action, and outputs the next state or observation. And this is very common today because it's very much corresponds to just doing this supervised learning problem that I talked about earlier. The thing that it's missing compared to the symbolic model is there's no sort of higher level symbolic structure here that a planning algorithm might be able to leverage. So that's sort of what you're giving up. You've got a black box simulator. It can spit out next states given current states and actions, but you don't have any other understanding of that model than that sort of functionality. All right, now the other major choice, which is actually a very important point in model-based RL in terms of the models you learn, are whether you're learning an observational model, I'm going to call it that, versus a latent model. So an observational model is going to be something like this. So it takes in the actual observation, it might be a sequence of observations and an action, and outputs a prediction of the next observation and the reward. And you can imagine that if you're able to do this accurately, well, you can just feed in that next observation into the input again. This would be called autoregressive prediction. Feed in an action, and you can simulate any action sequence that you want and get the rewards. And this is trying to predict observations from observations. And the challenge here is that it can be really difficult to do this. You can imagine what has to be done here is if it's a real video, for example, you're trying to produce photorealistic images. Whereas I think we have strong intuitions that the models in our heads as humans are hardly anything like a photorealistic rendering of the world. When we talk about models in the symbolic planning world, the blocks world has symbols like on AB. Well, that doesn't care about the color of the blocks or the exact placement of the blocks on one block on another. It's a symbolic, sufficient representation that is very far away from modeling the appearance of everything in the scene. So this people have tried doing this. It's quite difficult, and it hasn't really panned out as much as we'd like. So there's been some success, but limited success in model-based reinforcement learning. I'll show you something at the end on this. The other approach, and this is maybe the most, I think, important change in the last couple of years, maybe the last year and a half or so, that has led to some of the newest innovations and successes. So this is worth paying attention to. So we have strong intuitions that in our heads, the model of the world is not, picture perfect quality image generation, right? At least I can hardly draw a stick figure. But I have a pretty good idea of what's going to happen when somebody walks across the room, nonetheless. So what that intuition leads to is, we say that I have a latent state representation in my head of the world. And in sort of model learning terminology, what this looks like is you take the original raw observation and we're going to encode it somehow. So this is a neural network. This might be a convolutional neural network that's really good at processing images. It encodes it into some vector space, in Rn, where n might be a large vector, it might be thousands of dimensions. This is going to be our latent state. This is what we're going to reason about in the agent's head. We're going to learn a model over this latent state. So the transition model is also may be a neural network, but it's going to be operating over the latent representation as opposed to the observations. And also the reward function is going to be learned in terms of this latent representation. Might also be represented as a neural network. And we're going to keep on doing this. So what we're trying to learn is an encoder, a transition function on the latent representation, and a reward function on the latent representation. And that's what I mean when I say a latent state space representation. And some of the major advantages here are that this state representation, this latent state representation, doesn't have to be photorealistic quality. It might be something more like what we tend to write down in our symbolic planning systems, although we could never determine that because these are usually uninterpretable. Like we can't interpret what the network has for meaning assigned to the individual dimensions of this vector. But the learning process is going to try to learn to ignore aspects of the input that are not important to solving the planning task, not important to predicting rewards in particular in this case. So they can ignore background, in the video if that's not important, or whatever else they want to ignore. And so as long as you can train it so it can predict future reward in the latent space, regardless of what actions you take, you might as well just use this to plan with, right? So we have a way of jumping from our observations in the real world to states. So that lets us sort of translate from the real world to our internal world in order to take actions when we want to. But you might as well be planning in this latent space if you can predict rewards accurately. And this idea of learning latent representations seems extremely difficult because you're really not given any supervision on these latent representations. Like this would have to be learned in an unsupervised way in some sense. But this idea has been actually done successfully in a number of recent systems for things like Atari, for things like continuous control problems. And as far as I can tell, it's one of the key reasons why we're starting to see success in model-based RL now. All right. So that if there's one takeaway from this talk, I think that would be it. Latent state modeling is starting to become something that seems like we can do it to some degree. There's a lot of work left, but that has really led to maybe a revolution in model-based RL. So I'm going to just briefly talk about this. This is not terribly important, but the types of planners that you'll see in these systems are, well, tabular. We saw this. I'll show you some examples. Monte Carlo planning. This is Monte Carlo tree search. So if you only have a simulation-based model, as a, for example, a neural network, you can use it to produce trees and use some sort of tree search algorithm to make action choices. Symbolic planning. Sadly, there's been very little of this in model-based RL, but happily for you, this could be an opportunity. The other type of planner that I'll mention is, and this is actually the most common type of thing done in model-based RL these days, is you actually just use a model-free RL algorithm as the planner. So, if you have a learned model, for example, a simulation-based model, you can just, in the agent's head, run a model-free RL algorithm using this model to feed it experience and come up with a policy. And that seems like a very weak form of planning from a ICAPS style planning perspective, but that happens to be what people do the most in the reinforcement learning world. And this is partly because these model-free RL algorithms, the tools are sort of readily available, and partly because some of our best planners are not really applicable to the representations that can be learned. And another reason for this is a lot of work these days is in continuous action spaces, and that there are not many really good planners for continuous action spaces, whereas there's a number of model-free RL algorithms for continuous action spaces. So there's a few reasons why this is trending, but I hope it's going to be changing, and hopefully with a lot of your own work, those of you that are here watching this. All right, so now, we've I don't know how much more time I have, but I'm going to try to go through these. How much time do I have left?
You have 25 minutes, including discussions.
Okay, so I'm going to try to go through these and give you a high-level picture of some of these classes. So I'm going to start with this tabular model class, and one reason. So tabular model. One thing to note is that if I give you a whole bunch of samples, like if I give you a whole bunch of data of state, action, reward, next state, it's very easy to estimate a tabular model, right? All you do is for the reward function, you just, for every S and A that you saw, you write down what the reward was in the table. And otherwise, if you haven't seen it, you assign it an arbitrary value, maybe 0. For the transition function, you just keep track of how often I ended up in state S prime when I took action A and S, and you normalize by how many times you took action A and S. So these are just simple frequency-based model estimation techniques. You can get fancier. What I'm going to do is just show you, in theory, what the first major theoretical success was for model-based RL, I would say. So one of the big problems in model-based RL, in RL is exploration, right? You're in a giant environment, and you need to gather enough experience, right? If you gather enough experience across the entire environment and you estimate your model, you can solve it optimally, and that sort of solves the RL problem, right? But how can you be sure that you're going to be able to gather enough experience across all of the model? Maybe there's corners of the model that are hard to get to, but they're critical states for solving the MDP optimally. So the first sort of major success in theory, I would say, for model-based reinforcement learning was to solve the exploration problem. And it uses the idea of optimism in the face of uncertainty. And it leverages planners to plan your exploration. right? And this is very very simple. So what we're going to do is we're going to start with an optimistic model. And what this means is that you're gonna keep track of how much you've explored every state in the state space. And again, this is for tabular representations. And then you're going to, if it's not explored enough, you're gonna say, you're gonna pretend in your model that it gets the maximum possible reward, right? Maximum possible reward. And then you're gonna solve that optimistic model and follow the greedy policy for some amount of time and then update the optimistic model. And what that's going to do is the optimal policy and the optimistic model is going to try to get to new places because you're like, oh, I haven't been to France. Oh, I'm going to pretend that there's a pot of gold there. And now I'm going to solve the planning problem. I'm going to try to get to France. And the agent will try to do that. And if you get to France, you're going to learn something about France. You haven't been there before. If you don't get to France, that means your model was wrong because you tried to get there, but you didn't. And you're going to learn something else about some part of your model. And so basically what the end theoretical result is that this type of algorithm, this particular one's called Rmax, the Rmax algorithm by Brafman and colleagues, was basically the first, well, this was not the first one, but it's an example of a polynomial time reinforcement learning algorithm, right? Which means that you can solve reinforcement learning in polynomial time in the number of states and actions, where what this means is that the number of non-optimal actions that you take over the lifetime of the agent is bounded by a polynomial. So that was pretty exciting. And model-based algorithms were the first ones to give a theoretical guarantee of polynomial time reinforcement learning. So that's nice, but it seems very limited. It's kind of disappointing. I'm telling you about these tabular MDPs. Could this type of idea of using a tabular representation be used for enormous MDPs? Right? Could we do that? And I'm going to switch my slide deck here, and we're going to see that, well, you can actually, there's been some recent work that shows you can do that to some degree. So I'm going to show you some work on tabular representations. So one thing you could do is you could learn, this is sort of a general framework. So you have a set of data that you've collected so far by exploring the environment. And you could use, we're not going to get into details, but you could use different techniques and neural networks to come up with encodings, latent state encodings of the states. And somehow, I'll show you a couple of methods, compile them to a tabular MDP. You get a tabular model, it might have millions of states, and then run something like value iteration to get a policy. This is a general thing that you could try to do. Seems kind of crazy. But there's been a couple of ways of doing this in practice recently. So and then if you get in the real world and you're in a state and it's not in this tabular model, which is almost always going to be the case, you can use nearest neighbor type techniques to find the closest K states and average their results. There are some principled ways of doing that. So I'm going to show you one example. This is an interesting paper for you to read. It's too much to go into to talk about how they do this, but how they learn the representation is via this variational autoencoder. And the unique thing about this variational autoencoder, right? The biggest thing is it has an encoder, right? It takes an image and then it produces, in this case, a discrete encoding of the environment. So most autoencoders produce a continuous encoding. This one produces a discrete encoding by using some discretization methods inside the neural network. And so what that lets you do is you effectively can now map any observation to a discrete flat state if you want. And you could now compile an MDP over this discrete state space. You collect a whole bunch of data and you can connect this big graph together for these discrete states. So I'm not going to show you results from this technique, but this was one of the first techniques that showed some promise here. They showed some interesting, promising results in the 3D navigation domain. They also seem to have been able to solve some version of Pong and Atari, but explicitly said that it wasn't working for the harder Atari games. So it showed some promise, but hadn't quite got there yet. But it was really interesting because this is one of the first cases I've seen people marry deep learning, deep representation learning with optimal planning. So since I'm I'm the presenter, I'm going to talk about very briefly about some of our own work in this area. And I'm going to be giving a talk at the ICAPS workshop on RL and AI planning next week on this work. But this is another example. We were inspired by that previous work, but this is a very different way of doing something. So what we're going to do is to leverage optimal planning. So what we're going to do is we're going to take our experience database. This is just an example of Cartpole. We also work on Atari and other games. And we're going to build a data graph somehow. And what we're also going to do is we have a particular framework, this deep averages framework for filling in the unknown parts of this graph. And I'm not going to go into the details of this, but you can now fill in as you get new data, a probabilistic transition graph. And now you can solve this thing. So this MDP down here, this tabular MDP, is going to be roughly the size of this data set. So if your data set is in the millions, you're going to have a million state MDP here. Then you use value iteration to solve it. And what we do is we're able to define this non-parametric MDP that has a very crisp notion of what you do with unseen states. And unseen states are handled by sort of nearest neighbor lookups. And so essentially you solve this core part of the full continuous MDP, and it can apply to any state that we see. And in these states here, I haven't said it explicitly, these are, you can use any latent representation learning method that you want. And there's a bunch of them out there now. So these are often going to be continuous states. So what can we do? What does this show us? Trying to see what. Oh yeah, so yeah, this nearest neighbor stuff is based on some theory. So it is on sound grounds. So here's some results from Atari, and we're showing here results for only 100K transitions. So the data set that was created by 100K transitions of running the algorithm, which actually we're trying to get the size of the data sets we need to solve RL down. So actually this is a size that is desirable. But what we see here is the orange is model free, just think of it like that, and the blue is model based. We can see that we've got a significant advantage in most of the cases. This is sort of just as the algorithm iterates. We're using, just so you know, this is a model-free algorithm. It's called BCQ. It's kind of like DQN. And we're using its representation at each point with the data that was collected to solve the MDP. And we can see that we get a better solution by solving the MDP with planning than what it had at that point with the same representation. And this can scale. So I'm showing you results here for 2.5 million transitions. These slash lines are the model base. The solid ones are the model free versions. And so you can see there's quite a few advantages here. Sometimes it's about the same, but this is now getting in, we're solving 3 million state, in this case 2,000,005 state MDPs, and we're doing this with a GPU implementation. So this is practical now, and it lets you use any representation learning you want. And so it's showing some promise, and I think there's a lot of work left to be done along these areas. So I'll skip this, but basically what it shows is that the flexibility of doing model-based planning is, well, you can learn in the original problem over here. This is just like a goal navigation problem. Then we can say, oh, what if you can't turn left, or what if you can't turn right? you just resolve the policy under that constraint. No more learning required, and you get the corresponding policy. So that's sort of the power. All right, so I don't have much time, but I want to show you a couple of other frameworks. So probably the most famous example, and a lot of people might not think of this as model-based RL, but I think it should be treated as model-based RL, is the trilogy of AlphaGo to AlphaZero to mu0. And I'll go through this quickly because I think there's a lot of material online if you want to see talks on this work. David Silver has a number of talks on this work. But I'll try to give you a flavor of what this does and why we might consider it model-based RL. So basically, one thing that we want to point out is everything that I've talked about so far, whether it's model-based or not, you end up with a reactive policy in the end. What I just showed you, the work I just showed you from myself and the previous work for tabular representations, we ended up with a tabular representation of the policy, more or less, where you use nearest neighbor when you fall out of the table. And that's great, but it feels unlikely that you're going to get agents that do well at things like chess and Go, games or problems that seem to require real deliberation. Feels unlikely you're going to be able to do that by just representing the solution by some sort of circuit, a feed-forward reactive circuit. And so what we need is to be able to do deliberation. We want to learn to do deliberation. And those of you familiar with chess engines or just planning in general, when we say deliberation, we mean here's a current state, think about it for a while, build a search tree, and figure out what to do. And AlphaGo and AlphaZero are two examples of systems that do this. They're going to actually, at runtime, use tree search to actually solve chess and Go and shogi. They use Monte Carlo tree search. I'm not going to go into the details of this. There's 1,001 variations of it, but basically there are two parts. How do you expand? It's an iterative algorithm. How do you expand the tree on each iteration, and then how do you evaluate the leaves at each iteration? So those familiar with tree search, this is just a fairly common concept. And the catch is AlphaGo and AlphaZero, they actually assume a perfect simulation-based model to do this tree search in. And that leads to the question, should you consider it MBRL, model-based reinforcement learning? I would say yes, because even if I give you the rules of chess and Go, it's still quite a challenge to get something that can learn to play it well, and let alone a world-class level. So I'm going to call that reinforcement learning still. But what is left to learn, right? If we don't need to learn the model, what's left to learn, right? We just solve it with a planning algorithm. Well, obviously, we don't have planning algorithms that in a practical time can solve something like chess and Go optimally. So we're under time limits. And so what you need to do is learn knowledge to improve search under limited time. And there are at least two ways that you could do that, two types of knowledge. One, you improve the, let's call it intuition that is used to expand the tree, right? So you want to expand it in the most useful regions. You want to ignore stupid actions for the most part, or things that seem stupid. And also you want to learn to improve your leaf evaluation. This is like improving the chess evaluation function in a chess engine. So those are the two things that you could be learning via reinforcement learning. And both of those things can be done to some degree by learning. So in Go, this is an example of Go, the board position is input. You go through a deep neural network that tries to output probabilities of each move. And this sort of measures how good each move is likely to be. You could use this to prune the search tree, to effectively guide how the search tree is expanded. Like you're just going to not even consider all these actions with very low probabilities. You can also use it to evaluate states, right? So the evaluation of this leaf position would be sort of the best value of any action in that leaf position. And so, so what AlphaGo did was it initialized this neural network by learning from expert player moves, 30 million expert moves on the internet for 3 weeks. And it ended up being able to get a very high prediction accuracy, 57%, which is pretty incredible since there's so many moves. And then that sort of initialized the network, but then they used something called self-play to improve the network from there. So self-play, what it does is you'll start off with this initialized network, you'll play 1,000 games. And then during that game, you've frozen one network and you're learning with the other network. And this is model-free reinforcement learning. Then you're going to transfer this learning result to the frozen network. And now you're going to try to beat this network by learning for another 1,000 games. And you're going to keep on transferring the learned result and learning against it until you get to version 1 million. You've trained with an ungodly amount of CPU hours and actual money. And you get a pretty good neural network in the end, like a really good neural network for playing Go. It's still not good enough by itself to beat a world champion, right? You can't just use this network to make moves. But what AlphaGo does is it plugs this network into the search. There's 1,001 ways that you could do this. They tuned a particular way that worked well for their setting. And as a result of that, they beat the world champion in Go in 2016, which was an incredible feat. Now, you might say, but AlphaGo required bootstrapping from human experts. We'd prefer to learn from scratch, which is true. And that's where AlphaZero came in. AlphaGo did this self-play with only the neural networks making moves. What AlphaZero does is it says, oh, we're going to do self-play, but we're going to use tree search along with the most recently learned neural networks to guide the play during self-play. And effectively what this does is at any point, even if you start off with a random neural network, the tree search is going to help you improve your action selection over that network. So you get some network that might make some good decisions, but not perfect. Then you improve those decisions with search. And now we're going to learn almost with supervised learning, actually with supervised learning, to improve the good decision network based on the improved decisions that we observe. Okay, and this loop can go on and on and on during self-play, and it's sort of bootstrapping via search rather than human experts, right? Previously, we had to get off the ground by starting with human expert supervised learning and then doing RL with just the neural networks. Now we're bootstrapping with search. So this is a powerful idea, and they were able to also beat the previous AlphaGo. And finally, if we end the trilogy with mu0, AlphaGo and AlphaZero both assumed access to a perfect world model. mu0 is really interesting. I'm not going to go into the details, but it actually learns a latent space model of these games. So a vector representation of Go and chess, and it does all of its tree search, including learning the different neural networks to guide the search in latent space. And it's learning this latent space representation and all of the AlphaZero search control in parallel. So it's pretty remarkable they got this to work. But there's just neural networks everywhere now, right? You've got neural networks for the transitions. And so what this looks like is when you get a state, it encodes it into a latent space. Now it's going to build the tree over this latent space, okay, using this R and T. And now, as I said, we could learn also other networks to guide the search. And so you've got 5 neural networks here guiding everything. And this actually can be made to work just as well as AlphaZero and actually beat AlphaZero in some cases. And it requires a smaller network architecture. So pretty incredible. I think that sort of finishes off the trilogy of this line of work from DeepMind, which was really a landmark in AI history, I would say. All right, so finally, with the few minutes I have left, There's actually not a whole lot to say about this. It's pretty simple. So there's this third category of model-based reinforcement learning, which is maybe the most common category, but maybe the least interesting category from a planning perspective, which is we're just going to use a model-free algorithm as our planner. And what that means is we've got our real environment here. And we are interacting with the environment. We store the data from that environment interaction, and we can learn a model, right? Any one of these models that I just talked about. Usually it's going to be a neural network. And we can use this model to generate simulated data. Often this is called imagined transition data that we can feed the model-free algorithm in addition to the data from the model-based algorithm. And so the model-free algorithm gets to see a lot more data now that's generated from this learned model. And if this learned model was accurate, we would exactly be able to basically do model-free RL, but with lots more data. So I've got a question here. Is what you call a simulation-based model basically a predictive forward model? Yes. So when I say simulation-based model, I just mean it's a black box that predicts the next state or observation from the current state and observation, current state and action. Then I have, in the latent state model, you learn an encoder that maps observations to states and a neural net that gives the transition function. In general, how do you match st+1 given by this function with a state from the observation at t+1? Very good question. I wish we had time to go into this. This is actually getting into the details of how you do the latent state learning. The MuZero paper would talk about this. But one answer is MuZero actually doesn't try to match. So it's very interesting. It does not try to ensure that, okay, so if you take this real world, if you're in this real world state and you take an action and you end up in some other state, it does not try to ensure that mapping that new state with the encoder gets st+1. I think that will typically happen approximately. All MuZero cares about is once I map down to this latent state space, can I predict the sequence of rewards that result from any action sequence? And if you think about it, that's all you need to do if you're interested in just doing tree search. Right? As long as for any sequence of actions, you can predict the sequence of rewards accurately, it doesn't matter if this t+1 corresponds to what you would have got if you encoded the observation at t+1, which is very weird, I know, but it's sort of sufficient. There's other work that will actually try to enforce that what you see at time t+1 in observation space, the encoder actually produces the same thing as the transition function produces. So there is work that tries to explicitly maintain that consistency. But this is sort of on the forefront of research, right? So this is not, but people haven't really settled on the best way to do this stuff yet. So it's a very, very good question, right on the forefront of research. All right, so all we're doing here is we're supplementing the experience a model-free learner gets with experience generated by a model. And you get this for free in some sense at a computational cost, but not at a cost of transitions in the environment, which could be the more costly thing. If you think about robotics, for example. And there's 1,001 variations of this. I don't want to go into, of course, we can't go into it. I would say DynaQ is maybe the first discussion of this. This is in the 1990s. This is before the deep learning era. They use Q-learning or SARSA here. They would generate K imagined samples for every real one. And they showed some benefits to that. Another example would be this paper here, where this is one of the first examples of showing something working in Atari. Now they actually learn a model over the observational space, which requires an incredibly complicated network. Like most of the paper is about this network, and they use PPO, this standard model-free algorithm, to sort of train on the real data and the simulated data, where the simulations are actually an observation space. This works, it worked, it gave non-trivial performance in Atari, but it failed for the really hard games, for games that are more visually complicated, partly due to the poor reconstructions. It's really hard to do this, this sort of modeling function, this transition function in observation space. So this would be an example of a state-of-the-art algorithm, I would say, in this space called Dreamer. And here they're actually learning a latent space model, okay, rather than an observational model. And there's a lot of details that you could go into, but the one other interesting thing about Dreamer, I think, is somewhere, this model-free thing is somewhere in between model-free and model-based, in the sense that it's learning a neural network representation of the model, which is a differentiable function. And so even though we think of it as a black box function, it can still be differentiated. So it's not quite black box. And they leverage that to help improve the policy in a more principled way. And so what I'm gonna, this tries to illustrate that, but if this green is the latent state space, so let's say Dreamer does a trajectory of the current policy in the latent space, this green latent state space. It's just high dimensional vectors. And it's also predicting the value function and the reward function along the way. Well, it can actually, since this function is differentiable, this transition function, the reward function is differentiable, the value function is differentiable, they can actually update the policy parameters in a way that improves the policy, the reward that you could get along this trajectory. So it's going to say, how could I change the policy so that it's going to be more inclined to get high reward in this latent state space? And so in this way, it's kind of doing a little planning type step, but it's actually a little reasoning step to get policy improvement, which is more than a pure model-free algorithm. So, and it does well. You can look at the paper, but it's currently I've only seen results on continuous control domains. I think you could get something like this to work in Atari if they haven't already. As I said, there's papers coming out every day in these areas. So finally, you're all looking for research problems. I would say the big gap currently is there's hardly any model-based reinforcement work that uses structured and symbolic models. You're starting to see more of it, but we're really just at the fringe. And the people that I'm seeing do it are not really from the planning community. So they're not ever leveraging things like strips or PDDL or RDDL languages for, as we think of planning languages. So that there's more and more work around the idea of learning object-oriented models, which, like blocks or objects. It makes sense that you should have models that recognize objects, but they don't use sort of the types of planning techniques that we think of to leverage those object-oriented models. So this is a huge space. And I'd say there's very limited success so far in learning these models from raw data, right? You could say that what we want to do is, and similarly, leveraging those models with symbolic planning techniques. So I would say a research objective, if you sort of take the analogy of what some of us have recently done in the tabular case, like we learned a representation and compiled it down to a tabular Markov decision process and showed you could actually get some non-trivial results just by doing that. Like this is leveraging deep learning for representations, a latent representation, and then you compile it down somehow. Can we do this for more structured encodings? Can we get some latent representation that you can compile down to a satisfiability problem that encodes a problem, and then use SAT solvers, right? That's something that I want to work on immediately, and I hope some of you will look at things like that. Can we learn latent representations that compile down to something like PDDL, strips, or RDDL, and then use planners that we've developed in ICAPS, FF plan, Llama, Prost. Can we use those? So I think this is something that we have simply not demonstrated yet, but it's something that does not seem impossible. And so I guess I'll just end it. Where can we demonstrate the value of integrating ICAPS style planning and representations and deep representation learning? I think that's where we could really make a big impact and get the attention of the research community more. And I hope that I see more and more PhD theses coming out on this in the coming years. So with that, I think I will end, probably a little over time, but that, yeah, not
Thank
too
you.
far off time.
Thank you very much, Aaron. Thank you very much. I think we leave the rest of the discussion over the Slack channel because we are over time.
Yep.
And thanks again for this very comprehensive and inspiring talk. And we all hope to see a lot of further work along the gaps and directions that you set.
Yep. So yeah, just put questions on Slack and I'll be monitoring it, folks. Thanks a lot.